All right. Can you see the screen?
Yes, sir.
Okay. So in this chapter, we will discuss different mining techniques for data streams or data which comes like a stream. Okay. So let's go into that. So let's look at some examples of what we call streaming data. Let's say ocean behavior at a point. Behavior means there can be many things. Let's say temperature once every half an hour, or some kind of an interval. Then surface height once or more per second, which essentially can measure the fluctuation of height, right? So fluctuation of height will give you how high the waves are, right? So like tsunami warning or anything like that is something happening somewhere. Then several places in the ocean. So what you need to do is you need to then put in sensors in several places of the ocean. And how dense, maybe let's say even if you put 1 per 100 kilometer square, uh, that means it will be around 1.5 million sensors. I mean, I haven't done this math, it's from the book, but still it means there is so much of space in the world that it will be 1.5 million sensors. Okay. So all these, if people store, and of course there will be other attributes and so on, so that will make it a few terabytes of data every day. Then there can be satellite image data, right? So satellites are taking images all the time, right? So many satellites taking images of many different angles of the earth and other places in the universe, or sky all the time. So that will also be too much of data in terms of space. One can convert them to low resolution, but there are so many satellites and still there will be a lot of data, right? Then there can be web stream data, like more than 100 million search queries per day for the famous commercial search engines. Then so many clicks, everybody is clicking something, and people are trying to make sense of all of those, and so on. So as we see, streaming data comes from everything that are happening, or many tools that are collecting data all the time. Now, what is different in case of streaming data? What is different than what we are used to, right? So what we are used to is, we are used to getting a data set and then working on that. So it's like a standard static data. So there, the situation is that when we need, we have the data. Okay, I have, let's say, a few megabytes or a few gigabytes or whatever. I have some data, and when I need, I can actually get the data that I want. However, the scenario for streaming data is the data comes in one or more streams, and if you can process the data and store the results, whatever results you want to, whatever kind of analysis you want to do, process and store the results. And obviously, uh, the size of the results must be much smaller than the total size of the data itself. Uh, this is true for any general kind of analytics, that you have a large amount of data. Your analysis essentially means some way of summarizing or making sense of it. Unless you quantify into small attributes, you cannot actually make sense of it, right? So size of the results will be much smaller than the stream size in general. And yeah, so typically the results are some analysis, and once that is done, the data is lost forever. It's just like the river stream of water, right? So suppose some valuable things are coming along the stream in a river. If you can pick up a few of them and store it with you, but then the water flows and it's not coming back. So what kind of analysis you might want to do? There can be a few kinds of queries. Of course, it's not limited to only the kinds we are going to discuss, but we are going to discuss a few important ones. So the few kinds of queries, let's look at them. So let's say we want a temperature alert if it increases over some degree. Okay, it goes beyond some degree. What it means is that it may be on the ocean or somewhere else, right? So some temperature reading is being taken, let's say every minute or something like that. Okay, and if it rises above a point, then alert. Otherwise, you're not getting a result. So this is called, this kind of queries are called standing query. The query is always there. Give me my result when this happens. Okay, so this is a standing query. Then the following is like an aggregation. Maximum temperature in this month. Okay, maximum value of something that has happened or something like that, right? So these are not stand. These also are actually kind of a standing query, but you only expect it once in an interval. So sorry, so it's not really a standing query in that sense. It's a fixed time query. So you will get the result once once in some time interval. Oh, sorry. Yeah, and then there can be another kind, which is number of distinct users in the last month. So suppose in a web system or an app which has a lot of users, but not every user comes every month or every week or every day, right? So the number of distinct users today, number of distinct users in this week, and so on. Okay, so this can be another kind of query. Now, the techniques that we are going to see are not exact, just like the mean hashing and LSH we saw were not exact. The whole idea is that exact techniques, well, there are algorithms to compute them exactly, but if the data is too big, then doing it exactly is not efficient, or rather the data is so big that even efficient algorithms for exact answers will take a lot of time, which we don't want to afford, which we cannot afford, or we don't want to spend that much of computational resource. If we can get mostly good answers in a much spending much less effort, right? So computational effort or spending much less storage and all that. So that's why even if the data is not coming from a stream, but if the data is very big, right? And we always have computational power, which is at the limit, right? Which means you always want to process more data than your laptop or desktop or your server or whatever machine can process, right? So, so these techniques will be very useful, even if it's actually not a stream, but the data is very big. All right, so so let's go on to some of those. So the important tasks we will see in this chapter, two lectures I think will be enough. One is sampling from a stream, because we cannot afford to process the whole data. That means you will actually select a sample and then analyze that. Another is filtering from streaming data. That means, well, for every data element you want to accept or discard based on some condition. Then another is estimating the number of distinct elements in a stream without actually explicitly counting it. Another is estimating moments. Okay, so how much the data is varying, kind of. So let's start with sampling from streaming data. So let's say you have data in this format: user, query, timestamp. So some user ID, then what was the query the user posted, and then the timestamp, right? So something like this. You have a lot of, you have a stream coming like this, search queries coming in a stream in a search engine. Now, suppose a question is of this type: what fraction of the typical user's queries were repeated over the last month? Now, this is an actually English question, right? We need to understand what this actually means. So what fraction of a typical user's queries were repeated over the last month? Okay. And let's assume that we actually don't want to explicitly count that, and we actually want to count it only from a sample of 10% of the stream. Okay, it can be 5%, it can be 1%. Well, depending on how large the stream is and how little your capabilities are. But let's say, I mean, in this example, which will essentially describe the technique in a general case also. So let's say 10% of the stream. So now let's start on the technique. So the seemingly obvious approach, what would it be? So the question is, what fraction of a typical user's queries were repeated over the last month, right? So the word typical user is just, I mean, it's just like, don't look at users who post strange queries or something like that. In general, what fraction of the queries or what fraction of each user's queries were repeated over the last month? Now, one possibility, the obvious.
Just one question here. By typical user, you mean any user, general user?
Yeah. So obviously, will my query repeat in? So will I post a repeating query? So suppose I have posted 100 different queries in the last month. Maybe I have repeated 5 of them within the month. Maybe somebody else has posted 200 queries in the last month and only repeated 2 of them, right? So we need to kind of average this out, right?
Okay.
So I have repeated 5 out of 100. Somebody else has repeated. So obviously the answer will not be same for everybody. But if you want to kind of take a representative answer, what would you say? You know, that is the point.
Okay, so it's a representative answer.
It's a representative answer. Typical means a representative kind of an answer. Now, obviously, yeah. So it will actually become clear as we go on. Maybe the English sentence is not that very clear, but let's what it actually means is.
Means it's a kind of a set, and you are trying to figure out a representation of that set.
Yes. In a way, yes. But let's just go on, and it will be very clear. I mean, what we exactly mean. Okay, so by repetition, what we mean here is if I submit a query and you also submit a query, okay, then it's not repeating. But if I submit the query twice, then it's repeating. All right. Okay, so one possibility is you simply randomly select queries from the stream, right? I mean, that means for each query, you generate a random integer less than 10, 0 to 9. And 10% of that will be one of the numbers. So I mean, suppose 0. So if the random integer is 0, then you select that query, otherwise you discard it. I mean, instead of 0, you can choose 5 also, doesn't matter. So that's a seemingly obvious approach, right? Okay. So now, let's consider a scenario and let's see how this obvious approach would actually not give us the right answer. So suppose a particular user U has issued S queries exactly once and D queries exactly twice, and he or she has not issued any query more than twice. All right. Okay, so that means the total number of distinct queries the user has issued is S plus D, out of which D queries have repeated. So what we are, for that user, the correct answer is D by S plus D. All right. Now what we actually want is, if we went for an explicit computation, then for every user we will compute this and take an average, right? But we cannot do that. Okay, so what do we do? If we simply take a sample of the queries, okay, without thinking about which user it is coming from, then what will happen? So suppose you have this full stream. There are in particularly for this user, full stream, S query is issued once and D query is issued twice. Now, in an 1/10 sample, that means out of total whatever queries I have seen in this period, I'm taking a random 1/10 sample. Now, out of this S queries, S by 10 of those S queries are expected to appear, right? S by 10 of those S queries are expected to appear here. And for each of the D queries, each occurrence will be in the sample with probability 1 by 10, right? So each of the D queries, each occurrence will be in the sample with probability 1 by 10, but the D queries, each of the D queries are appearing twice. So since they are appearing twice, both occurrences will be in the sample with probability 1 by 10 into 1 by 10. Because we are taking a random sample, the probability that we choose a particular data point and another particular data point will be just the multiple, the this time that probability, this probability times that probability, right? So both occurrences will be in the sample with probability 1 by 100, which means no occurrence will be in the sample with probability 81 by 100. Okay. Now, look at this properly. 1 by 10, that means 10 by 100 for each of the D queries. Each occurrence will be there with 10 by 100, and both occurrence will be there with the probability 1 by 100. So no, the probability that none of the occurrences will be there is 81 by 100. Now that means one occurrence, so one occurrence will be in the sample with probability 18 by 100. So that is the probability of one occurrence being there and the probability of both occurrence being there, 1 minus this whole thing. 1 minus one of the occurrences will be there minus both occurrences will be there, right? So 1 minus, so no occurrence is the probability 81 by 100 and one occurrence is 18, so that will make it 99 by 100, and both occurrences will be 1 by 100, so the total probability is 1. Okay, so now what has happened? So once we have calculated these probabilities, now let's see with the 1 by 10 sample, if we calculate our answer, right? So what fraction of the queries are repeated? The correct answer for this user U should have been D by S plus D. Now from the sample, what we see is that S by 10 plus 18 by 100 D queries will appear once and twice will be D by 100, right? So the total fraction will be, if you sum them up, okay, so if you not sum them up, the queries appearing twice will be D by 100 by this S by 10, this thing, right? Total is, it will become D by 10S plus 19D. So what should have happened is D by S plus D, and instead what we have is D by 10S plus 19D, which means a denominator is much larger than what we wanted. So what is actually going wrong here? Our query is, for a typical user, what fraction of the queries are repeated? That means the repetition is counted only if that user himself or herself repeated the query. But if we simply take a general sample without considering the user, then we undercount the repetitions hugely, right? So this is actually a problem. So then what should we do? How to take a representative sample then? So the idea here is sample the users and not their queries. Instead of taking 1 by 10th of the queries, take 1 by 10th of the users, and for the users whom you are choosing, take all their queries. Okay. Obviously, this may mean that your total sample size may not be exactly 1 by 10th of the total data, but it will be around that because you are randomly sampling users, which means in some cases that some user may be a very heavy user and some user may be not so heavy user. So, the sample size will be more or less 1 by 10. So then how would you do it, by the way? So what we will do for the selected users, we will take all queries. Now how to do this from a stream? This means we will select some users. So as the data is coming, the previous sampling was easy. For every data element, we decide based on a random number, should I sample this or not? right? So that is an online at the time we see the data, we can quickly decide and either keep it or discard it kind. But now it's a bit more complicated. As each query in the stream arrives, we need to determine whether the user issuing the query is one of our chosen users or not. If the user is a chosen user, then we'll keep that query. If the user is not chosen, then we'll not keep the query. But whether the user is chosen or not, that depends on whether we have chosen the user before or not. So then it becomes more complicated.
Sir,
Yes.
I have a question. So there may be a problem. For example, suppose we have a stream of queries, right?
Yes.
So we are taking 1/10 of the users and taking all their queries.
Yes.
So it may be the case that 1/10 of the user population are generating 90% of the queries in total.
Right. I mean, that's what I just said. So it will not be the case that we will actually take the total sample size will be exactly 1/10. So it can be less or more. But well, so this can definitely happen. Only 1/10. So there may definitely exist a particular 1/10 sample of the users who are generating much more than 1/10 of the total number of queries. But you are not actually choosing that, right? So the probability of that happening is also very less, right? So you are actually going to sample the users randomly. So I mean, the probability of that happening is very, very low. Now, so one can always keep windows, right? So limits on the sample kind of number of queries we are getting in, and if it overflows that limit or something like that, one can cut down on 1/10. So you can suddenly decide, no, I cannot do 1/10, I have to do 1/5. So these adaptations are possible. Okay, but yeah, I mean, it is true that it may not be exactly 1/10 then. Now, for a more practical purpose, from a huge amount of data, you actually don't choose a 1/10 sample, you actually choose maybe 1/100th or 1/500 sample or something like that. So then the probability of that actually generating majority of the data is very low. But in any case, it can happen that the data that particular sample of user are generating are much larger than you expect. So, all right. So selecting queries for chosen users. Obviously, the algorithm should now look like this. For each query arriving in the stream, check if the user is seen before. Is the user a completely new user to me, or is the user seen before? If the user is seen before, then check whether the user was chosen when he or she was seen. If chosen, then keep the query. Okay. If not, then discard the query. Fine. Now, if the user was not seen before, then determine whether you will choose this user or not. Right? So this is okay. When we see a new user, I mean, we'll just do the general, 1/10 sampling or whatever sampling, right? So generate a random number in the range 0 to 9. And if the integer is 0, keep the query, put the user in the chosen list, and otherwise discard the query, right? So this looks like what will happen. Now, the problem here is here. Can you see my cursor, my mouse?
Yes, sir.
Okay, good. So the problem is here, checking if the user is seen before, if the user is chosen. Once you have done this, then the rest are like, just yes, no kind of thing. So how to do this? So checking if the user is seen before. Now, if the number of users is small enough, then you can actually keep their user IDs in a hash table in main memory or something like that. And a quick lookup, right? So that's quick, no problem. But what if the number of users is very large, right? So then what we will do, our choosing criteria is that we choose only 1/10 of the users. Now, but for every new users, we generate a random number, and every time we generate a random number, it will give us a different thing. So if you try to determine this by generating random numbers, then the problem is, suppose I am one of the users and my queries are coming in the stream. The first time the algorithm has seen my query, it generated a random number. Later on, when it again saw my query, it will again generate another random number, and these two numbers may not be the same. So it is not helping the algorithm to determine whether this user was seen before. However, random numbers cannot do that, but hash functions can. Hash functions which will simulate a random mapping, like we have seen in the previous chapter several times, right? So it will simulate a random mapping. So what will a hash function do? In this case, it will map one user ID to a random integer in the range 0 to 9. So the difference from generating a random number is, well, it is still random, but random given the integer. So given the integer, given the user ID, it is fixed. So before you knew the user ID, it is random. It has no relationship with the user ID, but it is for one particular user ID, it's still a function. For the same hash function, will send the same user ID to the same value every time. Okay. So then what we can do, when the query in the stream arrives, we'll hash the user ID. Hash the user ID, will get a hash value. If the hash value is, let's say 0, 0 is our selection value and all the others are non-selection value, then we select the user, otherwise discard. Now, why will it guarantee that this will do the job we wanted? Because, well, if I saw this user ID before, I have used the same hash function, and the value must have been 0 in that case also. And if I have not selected it before, I will not select it now also. So the whole idea here is transforming the criteria of choosing into a function, into a randomized function. Okay, so this is basically the idea of choosing or checking if the user is seen before or chosen. So let me go back to the previous slide once more and just mention this to you. So here, check if the user is seen before, we actually bypass that. We don't need to check if the user is seen before. What we will do is, if the user is seen before and chosen, I will choose again. If the user was seen before and not chosen, I will not choose. If the user is not seen before, then I will do what would be done in any case, right? So essentially, this is the central idea here, user hash function, which will randomly map one user ID to one of the integers. So what is the randomness here? The randomness is, given two different user IDs, I cannot tell which one will go where. That's the function is random, but the calculation of the function is such that, okay, but it is still a function. So if A goes to 0, then A will always go to 0, and if B goes to 5, then B will always go to 5. Okay, is this part clear? Okay, I hope so. So basically we just saw one case of one case of the technique for filtering with sorry, not filtering, sampling on streaming data. Now let's actually discuss a bit on this. We essentially saw one example, and which means that depending on what is your query, you should sample your stream accordingly. Here our query was, oops, sorry, I share again. Yeah. So here our query was, what fraction of a typical user's query was repeated. Instead, if our query was, what fractions of the queries are repeated, then we would not have to go for this complicated sampling, right? Then we could simply, do this first thing. For each query, generate a random integer. If it is less than, if it is 0, take it, otherwise discard. So essentially, you have to figure out what is the query or what is the analysis you are doing. Based on that, you have to be careful about choosing a representative sample. So that is essentially your take-home idea from this part. Now, the next part is a lot more interesting. Sorry. So next part is interesting, and it's actually one of the quite famous techniques in data mining, that is Bloom filter. So this is used for filtering streaming data. Let's say the task is filter part of the stream based on a criteria or condition. Okay. If the criteria can be calculated, then it's easy, right? So basically, example is filter all words starting with AB. Okay, so let's say a lot of queries are coming, lots of words are coming, only keep the words which are starting with AB. Then it's easy. You see the word, check, and keep it or discard it, right? Now, the challenge comes when the criteria involves a membership lookup. That means, like the previous one, in some sense, have I seen this before, or is this element one of my members? Right? So lookup query, is this element already present in my database? Right? So that's the query which is more difficult. Because your database can be very large, and each lookup may not be efficient. And if the lookup is not efficient, then, I mean, for example, the time taken to do the lookup may be more than the speed of the stream. So then you have a problem. So let's look at this particular problem. Let's say you have emails, email address, and email coming in a stream. And the task is filter emails based on email address. I mean, it can be a basic spam filtering to start with, right? So block list filtering, right? Something like that. So let's say we have a set S, set of 1 billion email addresses which are not spam. Okay. You let one email from one of these email addresses pass. Otherwise, you keep it in a spam or keep it in a waiting folder or something like that, right? Let's not discuss whether this is the best way of detecting spam. No. So there are lots of advanced machine learning techniques there, but this is a filtering technique, right? So it's a one pass thing. Instead of email, you could do many other things there, right? So this is just an academic example of what would you do in similar situation where you have a set which are your set of your members, data are coming in a stream. For every element, you have to check whether the element is one of your members. If yes, you keep it, otherwise you don't keep it, right? Okay. Now, so yeah, one possibility is that if it's one of your known email addresses, then you let it pass, accept it. If it's not known, then you run it through some sophisticated spam detection algorithms. You don't want to run it through the sophisticated spam detection algorithm for all the emails. There are too many. So you want to essentially, have a whitelist or something like that. So how would you do it? So we have this data, emails coming in a stream. The task is filter based on email addresses. Now we have this set of 1 billion email addresses. Okay, and this is what we have to do. Now, let's take a stock of our computing power. So each email could be 20 bytes or more. Email address, okay? Each email address could be 20 bytes or more. So if you have 1 billion email addresses, then the total could be greater than 20 gigabytes. Now, option one is you make a disk access. You can put this into a B+tree kind of a thing, okay, for each stream element and check. Okay, if you have not done B+tree, it's just a one efficient tree structure which can be used for searching quickly. I hope you have done that. Option two is what we will see today. Use a Bloom filter. It will not be exact. It will be a bit probabilistic. But what will happen is use a small amount of main memory and do it actually in main memory. Okay, you don't actually have to do disk access. So it will be much faster than option one. So again, I mean, in this whole chapter, it will be through hash functions and hash functions. So recall now what we will do here is we will actually go through some main points of what hash functions are good for. So a hash function would be a function from a set S to a set H hash values, which maps elements of a set to a set of numbers or values. It should be efficient to compute. It should be very quick to compute. That is one point. Then it should uniformly map the keys. That means each value is equally likely for each key. Okay, so it should be like once the function is fixed, it is fixed, but before that it should behave random, right? So let's say I have 100 different values, 100 different keys, and 10 different buckets to go to. The function should behave like a random assignment of the 100 keys into 10 different values. Okay, so that's the one. However, it is a function, so given h, the hash of any particular key is fixed. So once you have done that, if you repeat it, it will do the same thing again, right? So which means if x equal to y, then hx equal to hy. However, the converse may not be true. Of course, what can happen is two different elements go to the same hash value. What can be the choices of hash functions? Let's say a set of integers. We have actually done a bit of this in the last class. Hash uniformly to 5 bits. Okay. So which means the numbers will be 0 to 31. So if you fix a and b, then for each x, you can map it to ax plus b mod 32. So last class we saw, some 3k plus 1 mod 10, right? So something like that, right? So the intuition is the random choice of a and b ensures random mapping for each x. For example, set of w words, set w of words. Now how do you map integers? Integers are clear, right? So hx equal to h of x equal to x plus b. But what if they are not integers? What if they are words? What if they are email addresses? Still we have to suppose send them to 31 different or k bits, right? So which means 2 power k minus 1 different values. The same approach, but how do we compute ax plus b when x is not an integer? The one possible approach is take the ASCII value of the first character of x. That means if you have a word, take the ASCII value of the first letter or first character of the word. Now the question is this random enough? Well, nowadays everybody keeps names with the letter A. 50% of the people have the name starting with A. Okay, I'm just telling you my experience from the school school names, 40 students of my son's class and all that. So then it's not really random, right? The first character may not be completely random. So then take last two characters. Okay, so choose some fixed character positions. Okay, and maybe take the sum of the ASCII values or something like that, right? So what if those choice of such positions does not ensure randomness? Then you have to form an approach which will use all characters of the string x. So essentially, you have to first transform an approach which at least you are convinced that your given data, for your given data, it does not have a correlation of basically the given every data point, you cannot predict with some high probability that it will go to some particular number, right? So essentially that's the idea. So this is a bit of work here, and this should be customized to your data. That how do I get to the integer, and then we'll apply ax plus b mod whatever. Okay, so having done this much of background on hash function, so basically our technique will not discuss this detail. This was important because we have been hearing about hash function all the time, but then in practice, if you have to implement checking, are you getting duplicate words? Have you seen this before, kind of thing? What would be your choice of hash function, right? So essentially, then you have to choose this wisely. Now let's do filtering email stream with one hash function. Just like mean hash, similarly before, it will be similar. We'll do one hash function first, and then we'll combine multiple hash functions in a way, and then we'll do some probabilistic analysis. So let's say our available memory is n bits. So 1 GB is almost equal to 8 billion bits, right? So which means n bits will give me an array. So if 1 GB is my memory, then I will have an array of 8 billion bits. I have a bit array of 8 billion bits, right? So I will have a bit array of 1 GB, large one. Of course, here we don't have 8 billion bits, but it's just an example. So now we know now how to define a random, how to choose or construct a random hash function which does the following: hash each email address randomly and uniformly to one of the n bits. Okay. Equivalently, AH is a hash function from the set of email addresses to so from the set of email addresses to 0 to n minus 1. Okay. And it maps each email address to one of the n bits of the array. So now what we will do, we'll train the filter with known email addresses first. Now the word train, don't confuse with machine learning training. Okay, it's just like, we will prepare the filter first. We'll pre-compute the hash values of S. S is my set of whitelisted email addresses. So we'll pre-compute them. Now each email address goes to one of the bits. Okay, goes to one of the bits, one of the positions. If an email address goes to one of the bits, then we'll make it a 1, and we don't do anything to the others. So suppose one email address goes to this bit, then another email address goes to this bit, another email address goes to this bit, and so on. All right. It can happen that multiple email addresses go to the same bit also. Okay. So there can actually be an overlapping, no problem. So now we have our bit array, of which some are 0. Yes.
Sir, one question. This bit array you are talking about, is that n bits equal to 8 billion bits? Yeah, this n bits.
Yeah. So what we started with is, suppose we have 1 GB memory.
Okay.
And 1 GB memory is 1 GB is about 8 billion bits.
Okay.
Okay. So if we can, so this bit array will be in our memory. Okay. It will not be a disk or something like that. So
okay, fine.
It will be in memory. So if we have 1 GB memory, then it means we have a bit array of size 8 billion.
Okay, fine.
Okay. So basically we are talking about n, small n here, but that n in practice can be like 1 GB or it can be like 8 billion.
And you are mapping one email address to each of these bits of this 8 billion.
Every email address goes to one of them.
One of them, and sets that bit to 1.
Sets that bit to 1.
Okay.
Okay. So every email address goes to one of them randomly though. Okay.
Yeah.
The first one goes to 1, second one can go anywhere else. Okay. So then we set it to 1. Once we have set it to 1, it remains 1. It's possible that more than one email address, different email address can go to the same bit also. It's just, it just stays 1. So for example, if another email address goes to this bit, it is already 1, I keep it 1 itself. Okay. You don't do anything.
Okay.
So now what we have is, we have, having done this for my whitelisted email addresses, that means my set of members, having done this, I have a bit array which has some zeros and some ones. Now, the filter will work in the following way. So the filter has the following property: that a bit array with the hashed bits are set to 1. A bit is 1 if a bit is 1 means that at least one element A of S has been hashed to that bit. It can be more than one element, but at least one of them have gone to that bit. And if a bit is 0, that means no element of my member set has been hashed to that bit. Okay, so this is what we know about this bit array now. Now, when the stream comes, what do we do? A new data point, that means a new email address comes. New means, well, just a new in the data comes. We again do the same hashing, same function, hash the new data elements with the same hash function. Suppose X, it hashes to this. Now, if it goes to a 0 bit, that means X was certainly not present in my member set, right? Because if it has gone to the 0 bit, that means that bit is 0, means no element of S has to that bit. If I have seen X before, if I have seen if X is one of my members, then I must have set this bit to 1. So if it goes to the 0 bit, then I certainly know that it is not one of my members. So I can discard it, right? So I can discard or put it in the second list. However, if another element Y goes to 1 bit, then what do we know? Then all that we know is Y was possibly present in my member set, but we cannot be certain, because it is possible that different email addresses go to the same bit, right? So that's what we have here. Because two different elements can be hashed to the same bit, which means yes, I will accept the email, but there can be some false positives. So I may think, yeah, this was present in my members set, but it may be wrong. So obviously you see what's going to come next, right? What is going to come next? A probabilistic analysis of how much can we be wrong and how can we improve it. So let's go a little bit further on this today. Maybe we'll not finish Bloom filter today, and that's good. We'll actually recap a bit and finish the analysis in the next class. So we need to get control over the false positives, right? So you remember the mean hashing. We wanted to get control over the threshold of the mean hash, the probability bounds. We need to get control over the false positives. We need to quantify exactly how much error are we going to make and so on. So suppose an email address is not in my member set, but it is possible. So obviously what we saw before, we are not going to have false negatives. If we decide that something is a negative, then it's definitely a negative. So what can be there? It can be a false positive. So suppose it's actually a false positive. That means it is not in my member set, but it is possible that it is hashed to a bit that is already 1 for some hash function h. Now, if we take many such hash functions, can X qualify as a false positive every time? Unlikely, right? So of course the chance of making a mistake is there, but should not happen every time. So what we will do, we will use many hash functions h1 to hk, but available memory is still the same. Okay, available memory is still n bits. We will not have 1 GB per hash function. We will still have 1 GB memory only. So what we do, we overlap the filters for all the hash functions. So apply the hash functions on elements of S and set hashed bits to 1. If some bit was already 1, keep it 1. Now, so again I repeat, you overlap. Every hash function is going to give you a bit array like this, just we have seen before. We actually overlap them. If a bit is already 1, we keep it 1, right? So we do kind of an OR. If a bit is 1, what does it mean now? If a bit is 1, that means some X, one of my members, got hashed to this bit by some hash function hk. All right. So some S got hashed to this bit by some hash function hk. So like it's possible that I have h1 which sets these bits to 1, then or we do an OR of h2s, h2n, so on. So I have more bits become 1, right, and so on. Now, so what do we do when we filter? So we have this bit array now, and one bit, some bit is 1, some bit is 0, means that no element went to this bit for any of the hash functions. So this is definitely a negative. So we don't actually have a problem with the negatives, but we have a problem with the positive decision. So if some bit is 1, then some element has gone to this bit using one of the hash functions at least. So now if I see a new element y, what do? We hash the new element using all the hash functions h1 to hk. If the bit is okay, it will definitely go to different bits, right? So H1 will send Y to some bit, H2 will send it to some other bit. All of them must be 1, and then I accept. Even if there is at least a 0, then I reject. At least a 0, then I reject means, well, it couldn't be there before, because if I have seen this before in my members, then I would have already set that bit to 1 for that hash function. So I will only accept if it goes to 1 for all the hash functions. If it goes to 0 for any I, then the element is certainly not present in S. Now this is obvious that because Bloom filter does not produce any false negative. However, there would be still false positives, and yeah, so there will be still false positives, and we'll go into the analysis in the next class. Again, sorry, when I do this window while sharing. Yes,
Hello?
somebody has a question.
Yes, sir. It may be the case that after taking the union of all the hash values, so all the elements in the array are 1. So in that case, the chances of false positive will increase.
Yes. So if your majority of the elements are 1, then you have a problem. So what we will do actually in the next class when we do that, that means the obvious approach is your bit array size should be large enough, right?
Yes.
So there is actually, when you do the probabilistic analysis, we'll actually see a relationship between what should be our size of the array, how many hash functions should we take, and how many elements do we have, and all this. So we'll actually have a clear relationship, all of these things, so that we can take a decision about when it will work. Obviously, if your bit array has size 30, then there is no point. I mean, eventually all of them will become 1, right? So everything you will accept. Yes. So we'll see that in the analysis. So just to remind you, here, essentially what we are doing, we are overlapping, we are doing an OR of the bit arrays while constructing the filter, and while using the filter, we are doing an AND, like we must have all the, this element must go to a bit 1 for all the hash functions. Okay. So we'll do the false positive analysis in the next class and continue on further topics. So any other question as of now?
Sir, just I didn't understand what is the significance of this. If h of I y is equal to 1 for all I is equal to 1 to k, then accept. So this one, can you explain?
So this is just making the previous. This is just, so our, with one hash function, our condition was that if it goes to a 1 bit, then it is possibly present, right?
Yes,
We
sir.
would like to accept it. We are just
Yes.
making that condition stronger.
Yes.
It's not enough that it goes to a 1 bit for one of the hash functions. It must go to 1 bit for all the hash functions.
Okay, sir.
Just making it stronger, and we'll actually quantify how the probability works out in the next class. So exactly how this happens. All right.
Okay.
Okay. So yeah, so fine then. I think, okay, let's stop recording, and